protocols, right? We've looked at this a bunch of times, but this is kind of what we're going to see if we can find this kind of protocol in the data sheet, right? I'm saying, I told you guys that a lot of chips that I've used at least go along this protocol where you first send over the slave address of the master, of the slave you want to talk to. The master does this, and then you are telling the master what address inside the slave chip you want to read from or write to. And in this case, it's reading from because you have to issue another. Because we had to write over that register address, we had to issue a write command first, and then another start condition and a read command, and then read the data that you wanted. And this first data byte is sitting at register 2. The second is register 3, register 4, register 5, right? And then the way that changes with I2C, when we want to just write to the device, we don't need to do the additional slave address. We just say, hey, I want to write to this, and then this would of course be a little different, and you would write out the data that you wanted to. And most devices auto increment, but you'll see today a chip that I am looking at, maybe it looks like it doesn't auto increment. So you got to look at your different chips, read the data sheet to find out what's going on with each of your chips. So let's look at a couple I2C chips. Let's see here, and try that. Let's look at this. Where's it at? The temperature sensor. Sure. Let's do this temperature sensor. Okay. I happened to go down last night. I was looking for this lecture. I saw here are its registers. Not too many in this which makes sense, right? A temperature sensor just giving you the temperature. You probably wouldn't have too many configurations for that temperature sensor and all that kind of stuff. But this guy has these 3 registers, whatever they, well, obviously the temperature result, that's good. But then it's got a configuration register. And notice each of these registers are 16 bits. That's kind of interesting. That's a little different for I2C, but you're going to see in a second when we look at the timing diagrams, we still only communicate 8 bits at a time. So we always do, at least with the original version of I2C. And then I guess there's some limit, I don't know. Anyway, we have to read the data sheet more to figure out what those things are. Okay, so where do we find, let's see, I don't remember, is it up or down? Let's kind of look here. Here we go. Here's some timing diagrams. What do we got? That's an alert. Let's not worry about that one. More error handling. This is a reset. I don't know exactly why you would need that, but anyway, you'd have to read the data sheet to find that. Here we go. Here's looks like some good ones. Timing diagrams. This is, and notice, you know, see they run out of page space, don't you? Don't they? In the data sheet to do the good timing diagram. So notice these dots on the end, right? See, this is continuing the pattern here or whatever. What is this doing? This is a 2-wire, yeah. So I2C timing diagram for reading in Word format. Word maybe is 16 bits instead of byte, right? Word is usually 16 bits. That you got to be careful with that too. Sometimes Word is 32 bits. So you got to be really careful. Monitor that word. Anyway, that word, huh? Anyway, what do we do? So this is all continuing. Notice the stop doesn't happen until here. Okay, I don't think there's any other stop. There's not. So this is all one train of pulses, right? One communication to this device. And what do we do first? We have the start condition. And then we send over the address. We'll look at this, what these address things are down here. We'll look at that in just a second. And then we write low. Okay? So we want to write to this device. Notice what they do. They, frame 2 is the pointer register byte. Remember I kind of called that the register. They're calling it what register it's pointing to. You know, kind of same thing, right? What register do you want to read from? So you issue that, and then notice we do another start bit, or start condition is more a better way to say, and then we send the right address again with the read-write line high. Okay, so same thing, and then we've got to read. This is the way this guy works. You know, the slave device came up with a protocol. You read the upper 8 bits of that 16-bit register, and then acknowledge, and then you read the lower 8 bits of that register, acknowledge, and then stop. Okay? So that is very similar to the protocol. Well, it is. It's identical to what I showed you in that other timing diagram. Okay? But that's how you read this whole word. They have another timing diagram up here for 1 byte, I think. Yeah. So it looks very similar. Is this a read of a byte? Oh, this is a write of a single byte format. Maybe they don't even have a read of a single byte. Is that this? Yeah, I do. Right here. Read of a single byte. So why I guess maybe sometime, I don't know, why we just want the upper 8 bits of your temperature reading or whatever. Maybe there's a reason for that. Okay. Now, interesting, and then write is very similar. Write is like before. Is this a word? That's the read. Yeah, read, sorry. Up here, write of a word. Okay, you do the address, you write, you send what register, the point to what register you want to write to, and then you write out most significant bit, byte, least significant byte, and then stop. Okay? All right. So in other words, what you're setting up for I2C to talk to the DAN 28027. So don't get confused, right? The DAN 28027 has 2 ways to communicate with it. In the previous, in exercise, what was it, 2 or 3, whatever, exercise 3, we communicated to the DAN 28027 chip through SPI. Now for your project number 3 this week that you're going to work on in lab, you're going to communicate to the DAN 28027 also through I2C. Why did I do that? Again, I wanted to give you a little bit simpler interface than just jumping you right into the BQ32000. Where, I don't know, you could kind of say that the BQ32000 isn't that complicated either, but anyway, that's my method there, so that you did that. I guess I could have went and bought this temperature sensor. This would have been kind of a fun little sensor to play with, maybe. Maybe I'll do that in the future. Okay, but notice here their addresses, and let's see that. That's kind of interesting. They do a good job here because, again, one of the problems with I2C devices is if 2 devices pick the same address, you're in trouble, right? So they've been doing a better job. I've had trouble in years past where I've had that, where 2 devices would have the same address. But here, notice you can pick between all these different addresses by how you wire. There's 2 pins on this device, A1 and A0. Let's look at the pin out of this guy. Where is it at? Come on, where is it at? Here we go. So we've got our SDA and SCL lines for this temperature sensor. There's some alert. I don't know, maybe that's when a temperature gets up to a certain height, gets a certain level, and maybe you want to, shut off your CPU or something like that. I don't know. So some alert. We got a ground and power, and then we've got these 3 pins, address 0, 1, and 2. Right. Yep. Okay. Oh, and interesting. You can buy it in a version where you only have 1 address pin. Interesting. So this would have fewer options for what address you can select. Haven't really read about that, but that's interesting. Okay, so then by setting those address pins to certain values, and this is a little confusing. Oh, there it is, yeah. Oh, here it is, yeah, good. So you have your address 0, address 1, address 2. And, so you can wire address 0 to the SDA line. That's kind of interesting. I wonder how that all works. But in other words, it figures out its address on power up. And so it's not always monitoring the SDA line when that thing is going high, low, high, low, high, low. It's not changing. This is something that is determined on power up. Okay, so I think, yeah, maybe you could have little switches there, and whenever it receives address, maybe it checks then. I don't know. Anyway, but I bet it's something to do with power up. But you can imagine here, you can set up a lot of different addresses for this guy, okay, which is good. That also allows you to put more of these temperature sensors on your I2C bus too, right? You couldn't, if they were all the same address, you couldn't put 2 chips on your I2C bus. Anyway, kind of neat to see there. So that's a property of this chip. Okay, great. So there's one that kind of conformed to our format. Let's see, I think I have one more here. No, I have 2 more, that's right. So this guy, another one. Now look at this. So the way they write these timing diagrams, they don't even, because again, it stretches out over your page. Let's go see what this thing has. This is an IMU, another IMU chip. Oh boy, that's way up here. What's the pinouts on this guy? Here we go. So here we go. We've got our SCL and SDA. This chip is like the MPU 9250. It can also communicate over SPI. So it's got an SDO, serial data out, chip select, and all these. When you're using the SCL and SDA lines for I2C, you ignore these. You don't need a chip select. You don't need an SDO. Okay? All you need is the SCL and SDA. There's probably a default way you have to wire these pins down here, these 2 probably, so that you know, it knows to use I2C and not use SPI. I'm sure there's something like that in the data sheet. So we can interface to those. Now, I thought it had a way to do its address, but anyway, we'd have to check that a little bit closer. I thought there was something about address in there. But anyway, there's probably a way to set its address between a couple different addresses. You hardly ever see an I2C chip that allows you to set it to any of the 127 different addresses. Usually it'll pick like a couple of the bits, hard code, a couple of the bits of the address, and allow you to change a few of the n bits of the 7-bit address. Does that make sense? Because, you know, too many pins, that would, you know, require what? That would require 7 bits. That would require, you know, 7, well, not 7 I/O pins. It would require only 3. Is that it? No, 3 would be, sorry, 3 would be only 8 different addresses, wouldn't it? So you need, yeah, you would need 7. You would need 7 pins, right, to do all of those 127 addresses. So that's kind of wasteful. Normally you don't need that. Normally you hardly ever will use I2C where you use every address, all 126 addresses, right? Anyway, or actually 127, because 0 is not a address. 0 is an address for all the devices in I2C. If you want to talk to all the devices for some reason, you can write out to address 0, and all the chips will accept that. Okay, anyway, let's get back down to these timing diagrams. Was that it right there? Yeah, here's how you can set the different addresses right here, I guess. Oh, maybe you can write to it, it looks like. Okay, I'd have to read more about this. But anyway, okay. A little confused myself looking at this. So here is our protocol for writing here. Is that right? Now, let's see here. No, sorry. When master is reading 1 byte from the slave. And then, okay, and this is when master is receiving multiple bytes. All right, so what do we have here? We've got start condition, right? So the master issues the start condition. This is a nice way to do it without seeing all those clock pulses. Then the master sends out the slave address desired, or whatever slave address, with the write condition. Okay, that's the 7-bit address with write. If it's out there, the slave acknowledges. And this is like sub address or something like that. This sends over the register address of the device that we want to talk to, we want to read from. Then the slave also acknowledges. What's this thing? This is, right, this is the a repeat start at start, right? So the start for the read, in a sense, without a stop, right? So remember, we do a start and then send over the address, write the subaddress and then acknowledge, the slave does. Then we send over the address again, but now with the read bit high. And then the slave acknowledges and sends us data. And then either acknowledge, I guess you can do a no acknowledge here or something anyway. There must be some reason for that. And then a stop condition. Yeah?
Is the start condition and start read condition like the same for each device essentially? Like,
yeah,
it's due to your board?
It is, the condition is the following. It's always, and I want you to see this on the oscilloscope this week as you check off your stuff. The start condition is, notice here, let's see if we can show it here. When the clock is high, the data line does not move. It's only when the clock is low that the data normally moves, the data line with the I2C protocol. But when the clock is high, and the normal state of I2C wires, both SDA and SCL, is high. They're sitting high. And when the clock stays high and the SDA line is pulled low by the master, that is the start condition. Okay? And that's true for all I2C devices, the whole protocol. The stop condition is the opposite. The stop condition is when the clock line is high, the SDA goes high. Okay? That is the stop condition. Okay? Good. Good question. All right, back to our data sheet. Which one was it? It was this guy. Okay. So this is kind of a nice thing, but you being a new person to I2C, you're a little confused that 8 clocks are going across right here, aren't they? When you're sending over that data. 8 clocks are going across when you do this, the sub address, right? So you just got to keep that in mind. They're chunking that down and just showing to the different parts of the I2C protocol there. Okay. Anyway, and then don't read multiple bytes, right? You do the same thing, start, and then the address, what sub address you want to talk to, another start condition with a read of the address, get data, acknowledge, get data, acknowledge, get data. Oh, this is master acknowledge, what that stands for. Get your data, etc., and then a stop condition. And you could read many more than likely on most devices. Just read another byte, another byte, another byte, and it auto increments more than likely to the next register. Okay? Good. Now, looking at this next one. This one's for Reed. Reed is using this sensor for his graduate project for this class. And you picked a doozy. Let's see here. So it has a way to set its address. This chip is kind of interesting. It's a power monitoring chip. So I'm thinking you could also use this to monitor, power, but monitor if your battery is getting low or something like that. But this device has, the voltage in from the thing you're monitoring, the battery or your motor or whatever you're monitoring, the power of. And then you've got your data. And look at they talked it a little bit different. Yeah, I don't really know the difference between I2C and SM bus, but they're very similar. I don't know exactly the differences there. So sometimes when you see SM bus, that's also I2C. I don't know if there's there could be a slight difference. Then there's data and clock. That's our data is SDA and clock is SCL. So that's interesting. They label it differently. And then these 2 address pins that allow you to change the address as you want it for this device. But then we get down to the timing diagrams. Well, let's first look for the registers. There's only a few registers on this device. See if I can find them here. There's our timing diagrams. Come back to that. Here we go. So this one's also kind of like the temperature sensor. There's not too many addresses. Okay, so it's got one that's the configuration, sure. And again, we've got this device. It's a 16-bit. You think of this as a 16-bit register, but you can only send 8 bits at a time. So you have to send 2 8 bits to fill up this configuration register. Shunt voltage, don't know what that is exactly. Bus voltage. Bus voltage measurement data, so some measurement that it takes. And then it's got a power value, a current value, and a calibration register. Great. So there's only 6 registers out there, right? 0 through 5. So, oh, and interesting too, these 4 are only readable. I'm sure you could issue a write to them, but it would just ignore the data that goes over to them. Okay? So that also kind of, I don't know, it's interesting with the timing diagrams we're going to see in a second. It almost looks like it doesn't auto increment, but I don't know. We'd have to play with this and read the data sheet more. But notice when you go to their timing diagrams on this one, there's the configuration register. Yeah, so we got to go up here. So let's look at for write word format. This is writing read word format. What do I got up here? Yeah, okay, these are our start of our timing diagrams. So what do we got to do a write word format? Well, this looks pretty standard. You send a start condition, you send over your address, and then you say you want to write. Then you send over what register you want to talk to. They call, again, the register pointer byte, what register you want to talk to, and then you send over the most significant bits, acknowledge, least significant bits, acknowledge. Okay, so you write to your device that way. Now, what's this one? This is timing diagram for read format. Okay. Yeah, so this is what makes me a little suspicious here. Now we go and do the read, we issue this address, start condition address, and we have the read bit high. And notice that it then just reads. It doesn't say what register I want to talk to. Okay, so and then down here, notice that it has, this is for the, am I in the wrong one? No, I'm not. So there's also, an SMB bus alert. So maybe that's something different with this. Maybe there's some more error check handling with this SM bus. Maybe that's all there is there. But that's the alert. Where was the writing to the, here it is, right here, sir. Yeah, typical register pointer set. So notice here, it kind of looks like you have to issue this command with what register you want to talk to, 0, 1, 2, 3, 4, or 5, and then you have to do a stop condition. So just by looking at these, I haven't read through the text of the data sheet. Reed, you're going to figure this out, right? You'll tell me in a little bit, but in a couple weeks. But it looks to me, right, that you have to send over the pointer register. What do you want to register? You want to read forever, and issue a stop command, and then go and reissue this to read that register. So my question is, does that chip auto increment to the next register in there? I don't know. I don't know. That's something we got to read about, because maybe that stop condition down here isn't necessary. So data sheets are confusing. You kind of got to make guesses and you try things out. So the question is this necessary? If it's not, right, you could issue this without a stop condition and come up here just like we've been doing, issue another start condition with the read bit high and then read the data. I don't know. So that's something that's a little confusing by looking at the timing diagrams in this device. Okay. What do you think? I know this is really fast. This takes time. I just looked at this real quick last night, and but it's going to take. You would need to just read through the data sheet to figure out a lot of this stuff. So I'm just going on what I see in the timing diagrams and first guess in a sense. Then you have to take the time when you're working with this chip to really dig through the data sheet to figure out. And sometimes it's vague, and so the other solution is to wire it up and try it out and see what works too. Okay, give it a shot, see what makes this thing work. Okay,